All right, let's look at the next step in doing the process um, the of testing a hypothesis, what we call the traditional method. We'll practice with this problem. It's a problem that should seem familiar. I used it in the first video to talk about just the general idea of testing a hypothesis. And so just to remind you of this, 10 students were surveyed, and we found that 70% of them have enjoyed having their face-to-face class changed to online instructions. Based upon that statistical feedback, we made a claim that more than 65% of students have enjoyed the transition. And so, as you remember, step one is to write the claim in symbols. And so the claim's pretty nice. It's that last sentence. That's what I would suggest that you look for first. What's the claim that's being made? In all of chapter 8, there's going to be a claim being made. And the claim is that more than 65%. So they're making a claim about the percentage, and they're claiming that more than 65% have enjoyed the transition. We know that our null hypothesis is p equals 0.65. And we know our alternate hypothesis then, from what we were doing in the last video, is the claim unless it can't be, and it can. Right? And so I'll stick that 6 in there. And so it's exactly the same as the claim. So those are the first two steps. The third step is to calculate the test statistic. So these steps are in order. So once you write that claim in symbols, then you'll know you're making a claim about the proportion in this case, or you'll know you're making it about the mean, and that will tell you which test statistic formula to use. The test statistic formulas will be given to you in the book, and in 8.1 they use the one for percentages, and here's what it looks like. It is this formula. Z is equal to p hat minus p, all divided by the square root of pq all over n. And you know what? You have all of these numbers. It's so awesome. This z is the same z that's for a z-score, so you know what you're finding. You're finding a z-score. You're finding the distance between the sample value and this 0.65 in terms of number of standard deviations. But let's just go see. If we're familiar with all the notation, and we pretty much should be because we've used it all, p hat, you remember, is the sample percentage. So I'll write that over here on the side. The sample percentage, or the sample proportion, well, that was 70%. 70% is what came out of the sample, right? So this p hat right here is this 70% that's up here. It won't let me highlight it. I should have realized that I couldn't go up there and do that. So p hat is the sample percentage, and we know that that is 70%. P is right here. That's one of the reasons why most books have transitioned to this being the way that we write the null hypothesis, with the flat out equal to sign. And so that is a 0.65. And then be very careful down here. It's a PQ, so that's the same P, 0.65. You know what Q is. Q, well, let me write what P is. P is I'll put the number in the null hypothesis. Okay. And Q is always 1 minus P, so in our case Q is 0.35. And that's all over the sample size of 10. And you'll run that calculation by taking the 0.70 times 0.65 and then dividing that by the square root of 0.65 times 0.35 divided by 10. So be careful on how you put this in your calculator, but let me show you what you should get out for something like this. So I just grabbed a calculator. I didn't have one next to me. And so I'm going to run that calculation. So here I'll verbally describe what I'm doing. 0.70 minus 0.65, and I'm going to hit equals to get the 5% difference that I knew was there. Then I'm going to hit divide and get my square root. And then I'm going to be really careful in here. When I put in my square root, it comes with an open parenthesis, so I'm not going to use parentheses anymore. I'm going to simply type in 0.65, use the multiplication button, 0.35, use the division button, 10. And it's going to take the square root of that whole product and division, and then I'm going to hit equals. And I get a z value, 0.331. And so we're going to round all z values out to 2 decimal places, right? Because of the limitations that are in the chart. That is how you calculate the test statistic. What it is a measurement of how far 70% away is away from 65%. And so what we're finding is it's not very far away at all. It's only a third of a standard deviation. We know from our experience that that's not big. We were calling things significant if they were more than 2. And this is not even a third. And so this is a situation where the data doesn't appear strong enough to make a conclusion. But notice what would have changed if I had just, instead of basing this off of 10 students, let's suppose we got the same information with 100 students. If it was 100 students, if I found that I got the exact same number with 100 students, well, then z would be equal to 0.70 minus 0.65, all divided by 0.65 times 0.35, all divided by 100. And if I do it that way, if I take my 0.05 and divide that by the square root of 0.65 times 0.35 divided by 100, I get something stronger, but it's not really that strong, 1.04. So a little bit stronger, but not overall super strong in there. And so we can play around. So you can see that the number 70% now is farther away. But 1.04 standard deviations is not super far to be away as well. But I wanted to just show you that because as you change the sample size, you can get stronger numbers. Now, I made a huge assumption, and that is that it stayed at the original 70%. We don't know what's going to happen if I talk to 90 more students. And that's the reason why with the sample size that your data may not be strong enough to conclude. You don't know what's going to happen as you go and talk to more and more students. And so unless you're already separated from that 0.65 number, it's not going to be strong enough to say that there's, with the error involved in obtaining the 70%, that it couldn't have snuck down to 65% or even lower. So that's where we're at. So the one thing highlighted in this video that's new is this calculation that's right here of a test statistic. And again, it's telling us how far the value in the sample is away from the null hypothesis, which is the benchmark for what we're trying to claim. And so we're hoping we're pretty far away. And if we are, we'll be able to state something strong.